This is stochastic processes, module 8, renewal processes. In the first 3 lectures, we have discussed the renewal process and its properties. Then later we have discussed the important limiting theorems on renewal processes. Then we have discussed the Markov renewal process and Markov regenerative process. In between, we have discussed the reward renewal processes also. In this lecture, we are going to cover the non-Markovian queues with respect to the service time distribution. In particular, we are going to discuss the MG1 queue and the MGCC system. What is MG1 queue? In this queuing model, the inter-arrival times are exponential, but the service times are non-exponential, nothing but general distribution. Assume that the CDF of the service time is f of t with the mean 1 by mu. So suppose you assume that service time is exponential distribution with the mean 1 by mu, then it is a MM1 queuing model. Let Nt be the number of customers in the system at time t. In this model, the evaluation of the system after the arrival of a customer depends not only on the number of customers n of t, but also the remaining service time of the customers receiving service. The remaining service is nothing but, since the service times are random variable, the remaining service time is the elapsed service time or remaining or residual service time. Whenever the service times are exponential distribution, the remaining time or elapsed service time or residual service time all are exponential distribution. Whenever the service times are not exponential distribution, then the remaining service time will be a some other distribution. The evaluation of the system after the service completion depends only on the system of the state. In this queuing model, the system changes the state based on 2 types of transition epochs. One is the arrival epochs and the other one is the service epochs. First, we are discussing the arrival scenario. The evaluation of the system after the arrival of a customer depends not only the number of customers n of t, but also the remaining service time. Whereas the evaluation of the system after service completion depends only on the state of the system. Therefore, n of t is not a semi-Markov process because it depends on the remaining service time. Since after the arrival of a customer, the remaining service time also play a role, whereas after the service completion, it depends only on the state. If you recall the definition of semi-Markov process, the memoryless property will be satisfied at all time transition instants. The memoryless property will be satisfied at all time transition instants, then only the stochastic process is called a semi-Markov process. Therefore, here the n of t is not a semi-Markov process. Suppose the time origin is taken to be an instant of a departure which left behind exactly j customers, then every time the departure occurs leaving behind j customers, the future of n of t after such time has exactly the same probability law as the process had starting at time 0. So this is so called the probabilistic replica with the Markov property as well as the time homogeneity. If you recall the definition of a Markov regenerative process, a stochastic process has the property of a probabilistic replica with the few time instants. It has the Markov property with the time homogeneity with the few states, at few states. Therefore, n of t is a Markov regenerative process. Please refer the previous lecture for understanding the definition of a Markov regenerative process. So, by using the definition of Markov regenerative process, the n of t will be the Markov regenerative process if you consider the time epochs or departure time epochs. Let nth customer departure at the time instant Tn. Let xn be the number of customers in the system just after the departure instant of nth customer. That means xn is nothing but the n of Tn plus 0 just after the departure instant of nth customer. That will be treated as the random variable xn. Then xn comma Tn will form a Markov renewal process. The Tn are the time instant at the departure epochs, not the arrival epochs. Only the departure epochs, that collection of time points along with xn form a Markov renewal process, where xn is n of Tn plus 0. That in words, it is a number of customers in the system just after the departure instant of nth customer leaves. We can create a semi-Markov process by y of t is equal to xn if that value will be between Tn to Tn plus 1. If it is the same, then it will form a semi-Markov process. That means the system is not moving any other states in between the time duration. Then the y of t will be a semi-Markov process. As such, n of t is not a semi-Markov process, whereas xn comma Tn will form a Markov renewal process, and the n of t will be a Markov regenerative process. With the embedded, the y of t will be a semi-Markov process if I make y of t is equal to xn, where t lies between Tn to Tn plus 1, and having the embedded DTMC xn. Our interest is to find out the steady state measures. To obtain the steady state probabilities of yt, we need the one-step transition probabilities of embedded DTMC. Suppose these time points Tn are the regeneration points, then the Tn's will form a renewal process. Let An be the random variable denoting the number of customers that arrive during the service time of nth customer. That means xn plus 1 will be an plus 1 if xn was 0. If xn was greater than or equal to 1, then xn plus 1 will be xn minus 1 plus an plus 1. That is nothing but how many customers in the system when the n plus 1th customer leaves. That is same as when the nth person leaves, how many customers in the system. Minus 1 is for the n plus 1th customer himself. And how many customers enter into the system during his service, that is an plus 1. Whenever the xn was greater than or equal to 1. If xn was 0, then the number of customers will be in the system when n plus 1th customers leaves will be same as number of customers who enter into the system during his service time. Since the service times of all the customers have the same distribution, the distribution of an is same for all n. Therefore, you can go for all n, we can go for AR is the R customers enter into the system during the any customer. So that is the probability mass function of a AN. Now we can find out the transition probability of a system moving from the state I to J with respect to the stochastic process Xn. Xn is a embedded Markov chain in the n of t. So that will be Aj if j is greater than or equal to 0 and I equal to 0. Similarly, Aj minus I plus 1 or 0 according to the values of I and j. Now we can make a one-step transition probability matrix, that is nothing but the P. The row sums are going to be 1. Note that Xn is a irreducible Markov chain because each state is reachable by every other states. If you make a row that is nothing but lambda by mu is less than 1, lambda is the parameter for the inter-arrival time, which is exponential distribution. So whenever rho is less than 1, the chain is a positive recurrent. Rho is less than 1 is required because only then the mean recurrence time will be finite. Hence, the Markov chain will be a positive recurrent. Therefore, it is a ergodic. Irreducible positive recurrent gives the Markov chain is ergodic. Therefore, the Markov chain is the embedded Markov chain is ergodic. So we can find out the limiting probabilities that will exist as well as it is independent of initial state I. You can find out the limiting probabilities by solving V is equal to Vp and summation of Vj is equal to 1. The solution can be obtained by using the probability generating function of V's and A's. V's are probability vector, steady state probability vector, and A's are the number of customers arrived during the service of any customer. So Az is nothing but the probability generating function for Aj's, and V of z is nothing but probability generating function for the random variable for the probabilities Vj's. Now you can find out A of z in terms of the Laplace transform of the function f of t, because A of z is nothing but the summation of Aj into z power j, and you can replace Aj by the integration. Now integration and the summation can be interchanged, and f of t is nothing but the distribution of service time. F of t is nothing but the distribution of service time. Therefore, the small f of t is the probability density function of the service time. So the f star is nothing but the Laplace transform of f of t. So the probability generating function of A of j's is nothing but the Laplace transform of the probability density function of service time distribution. Now we can find the expected number of arrivals during the service time. That is nothing but, since we got the probability generating function, differentiate with respect to z and substitute z is equal to 1 will be the average number of arrivals during the any customer's service time. So you can simplify that by using the chain rule. So that will be nothing but lambda by mu, where lambda by mu is nothing but the rho. So the expected number of arrivals is rho. Rho is nothing but lambda by mu. Our interest is to find out the steady state probability. Probability is Vj's. So the Vj's you can relate in terms of by expanding V is equal to Vp, you will get Vj is equal to V naught Aj's plus summation form. So multiply z power j in both sides and taking the summation, you will get after simplification you will get Vz in terms of Az with the V naught. V naught is no custom. V naught is the steady state probability of no custom. Vz in terms of Az and V naught.